Welcome to today's lecture video on Chapter 6, Section 3. This is for AP Physics 1. The topic that we're going to cover today are listed up here at the top left, including our main focus, which is going to be centripetal force. We're going to take centripetal forces and we're going to apply that topic to two different types of curves, usually related to roadways, unbanked curves and banked curves. We've discussed this previously in class, but today we're going to put some math to it. All right, so let's dive right in. So first things first, we're going to be talking about the centripetal force of a motion. If we think about how things are rotating in any specific situation of your choosing, then we also have to remember that there are some major topics we've talked about before that are going to support this centripetal force idea. Specifically, when we talk about centripetal forces, we're going to reference Newton's second law again. Newton's second law, of course, says that forces in a system are equal to their mass times their acceleration. In this particular case, this same thing is true, except instead of saying a net force is the one at play, we're actually going to apply the idea that there is a centripetal force that is undergoing some form of centripetal acceleration, and its mass is going to matter in this particular case. So in order to calculate the centripetal force of a motion, we need to multiply a mass times a centripetal acceleration. Another thing that we want to kind of go over before we see an example is going to be that of unbanked curves and friction forces. So one of the things that we can assume about an unbanked curve, meaning a flat road. I think about going around any curve in like a suburban set of streets. These are going to be roads that do not have what we call a banked curve. Oops, my bad. AKA they are not raised. So if we're the person who's looking at this curve and this is like our eye, I know it's not a pretty eye, but it's an eye, okay? Let's say we're looking at the road straight on. What we would see for an unbanked curve is a flat line, right? If we look straight at it, we would see a flat line. If we were looking at a banked curve, which we will do here in a second, then we are looking at a road that has actually been raised. And by that I mean, if we look straight on it, we're going to see that one side or another has been banked, aka raised. This is really common on highways or where places where higher speeds are available. Okay, so highways, maybe back roads, things like that. One of the things that I'd like to point out for banked and unbanked curves. So unbanked curves, one of the major assumptions we're going to make is that the static friction is what keeps it from slipping. For an unbanked curve, for a banked curve, in fact, we can make an assumption that that there is no friction. And we'll talk about how to do this here in a second. First, I want to go over some of our examples with our Newton's second law in an unbanked curve. So just give me 1 second to zoom on out. All right. So here's an example. We want to calculate the centripetal force on a 900 kilogram car with a 500 meter radius at 25 meters per second. Okay? And this is going to be part A of our equation. Now, remembering that Fc equals mass times acceleration, we're going to need to figure out our Fc equals mac equation, and we're going to want to recall the definition for AC, which is v squared over r. In this case, because we weren't given an acceleration, we're going to have to calculate it. So, plugging in our values, we're going to get 900 times 25 squared over 500. This comes out to be about 1100 newtons, give or take. Okay? In the second part of the problem, we're going to calculate the coefficient of friction, static specifically, because remember we said with unbanked curves that static friction keeps the car from slipping. In order to do this particular problem, we're going to assume that all of the centripetal force that keeps the car turning is going to equal the friction force that's at play. I'll remind you that way back when we said that static friction was equal to mu Sn, n being our normal force. Since we are a system, aka a car, that is on I'm going to try to draw a car. This is the back of the car. The back. And we're looking at it. If we're looking at it on the road, we know that it has weight. We know it has normal. Okay? We're not going to talk in this particular case, but let's say that we're actually turning left on this. That means our friction coefficient is going to be the thing that's keeping us from, that's keeping us rotating, and then our friction is going to be pointing in the inside. And I'm sorry, my arrows are not the same, but they should be the same size, because we're saying that they are equal in this particular case. Okay, so this is a car turning left. All right, so by calculating, in order to do this, we're going to need to plug these two in. We know that in this case, that the centripetal force that we calculated in that first part is going to equal the coefficient of static friction times the normal force. The normal force, of course, being opposite of our weight, which, if you'll recall from our previous chapter, is equal to mass times gravity. So we're saying essentially this is the case. We're going to rearrange that equation to solve for the mu by doing this. And then we're going to plug some numbers in. We're 900 times 9.81. And remember that our coefficients should usually be less than 1. In this case, I believe it comes out to be about 0.13. There is no unit on a coefficient. Okay, so this is kind of an example of how to use that the unbanked curves and just the centripetal force equation real quick. Okay. The next topic for us to cover is going to be our banked curves. I'm going to come back down here. And with banked curves, there's a really nice explanation of why the formula becomes this. But I am going to go ahead and I'm just going to write out the final formula for our, ignore that part, for what a banked curve's angle can be found to be. So if we want to find the angle, this is the equation we would use to find it. Now, could we theoretically rearrange this to solve for V? Absolutely. That should be something you feel pretty comfortable doing. But if not, just kind of backtracking, we essentially are going to get this by taking the tangent of both sides, v squared over rg. Then if we're solving for v, we're going to move these things over. I'm going to get b squared equals tangent of RG takes the square root, b equals the square root of the tangent of theta times r times g. And I will remind you that you need to have your, if you're plugging in an angle into an equation like this, you do need to be in degrees. So don't get confused by the radians and degrees stuff that we've already done. I know that's easy to say, but in this particular case, since we are dealing with linear quantities, we should be in degrees if we're solving for an angle. We're not asked for radians, we're asked for angles a lot of time. 20-degree curve, etc., etc. So here's one rearrangement of the banked curve formula. Here's the one that actually solves for theta, one that solves for v. Again, could you rearrange to solve for r? Probably. These are the three quantities that are in here for you to solve are theta, v, and r. So I'm going to go ahead and I'm going to actually rearrange for r as well. Okay, so kind of taking this step and rearranging. I'm going to put r on the left side. And get r equals b squared over g times the tangent of theta. So if you have any questions on these banked curves, essentially these are the three formulas you can probably be using to help you solve those questions. Please don't forget that you can also use the previous stuff we've covered in class in this chapter, specifically concepts around centripetal acceleration, angular velocity w, and theta, so rotations and radians, in order to determine some of the information you may need to help you with this, right? So in some of these equations you see v. With a v, you can also be asked to solve from a w in order to get a final answer. Okay. So that covers everything from lecture for today. The practice problems I want you to do can be found in your on your book online. They're at the end of the chapter. I want you to do numbers 23 through 27. I want you to submit them today, but I want you to also know that we will go over them if we have any questions in class on when next time I see you. Apologies. Okay? Thank you.